Thank you all so much for being here on this very special day, where I'm going to defend my thesis titled Cellulose Accessibility and Reactivity After Cold-Alkali Swelling. But before we go into that, I would like to show my first ever poster. I was very proud, of course, so I had to take a picture. But what I didn't know that I was showing a picture of just some tape. Those of you working within cellulose knows that this is definitely not fibers. But a lot have happened since then, and together with my supervisor and co-supervisor and my amazing co-authors, sorry, so many co's, I've managed to publish 3 articles, and I also have 2 that are submitted and 1 that is a manuscript in preparation. And if we look at the titles from these articles, we can see that there's a very common theme. So it's safe to say that I've been thinking a lot about swelling of cellulose these past years. But before we talk about swelling, I would like to give an introduction to cellulose. So cellulose is one of the most abundant polymers that we have, natural polymers, biopolymers. And its structure is very simple. So it's a linear polymer composed of glucose units linked via the glycosidic bond. And we can get cellulose from the forest. And when we extract cellulose from the forest, we also get it together with other wood components, such as hemicellulose and lignin. But if we want a pure cellulose, we can get it from cotton. And then if we look at the structure again, we can see that there are a lot of hydroxyl groups, so that's the OH group sticking out from the structure. And with some chemistry, we can modify these groups, and then we call them cellulose derivatives. So we add functionality and we tune the properties of cellulose. And when we do that, we can get a variety of products. So we can get construction materials, paint, pharmaceuticals, and even plastic-like materials, and cellulose that is suitable for food-grade applications. Another type of modification that we can do is that we dissolve the cellulose and then we regenerate it. And then we call it, conveniently, regenerated cellulose. And then it has more of a textile-like properties. So we can make all these amazing things with a pretty simple structure. But even though the structure is so simple, there is actually how this structure organized within the fiber or fibril that gives it the properties, and what's actually why it has some reactivity or not. So what we can see is the cellular chains organize in a very specific and complex way in the fibril due to a lot of hydrogen bonding and also van der Waals forces. And it makes the fiber or fibril very tight and compact, and the structure is very dense. And therefore, the hydroxyl groups that we can modify are kind of hidden in the structure and not accessible. Another thing that can limit reactivity is the purity. So I mentioned that when we extract the cellulose from wood, we also get other wood components, such as hemicellulose, and those can further restrict the access to the reactive sites. And I also want to mention here that I say that this is a fibril, but this is just one way, or it's a very hot topic, so there are many types of how we look at how the change organizes. So this is called the diamond conformation. Together, all of these things can make the reaction pattern uneven, and also we can get a low reactivity. So what we typically do is some type of activation. So activation can increase the accessibility and therefore the reactivity, so we can get a better reaction. And in my case, I've been using alkaline activation to swell the cellulose. And we do this because we want to disrupt this hydrogen bond network, and we want to increase the distance between the chains and just make the material more disordered. But we have to keep in mind that when we treat cellulose with an alkaline or a strong alkaline solution, we can get some change in the crystal structure. And this is kind of a textbook example of how we think it looks. So in native cellulose, we have cellulose 1, and then we say that the chains are organized in a parallel manner. And then we treat it with our alkaline solution, and we get antiparallel chains, and we call this cellulose 2. So previously in our group, we have seen that if we do a cold alkaline swelling, and then we follow up with some reprecipitation, we have seen that this swollen cellulose has a higher accessibility, but also susceptibility to both enzymatic and acid hydrolysis. And when I talk about swollen cellulose, you might wonder, what do you mean? Because it's hard to imagine, but I have some pictures here showing how swollen it is. So this is the reference material and the swollen cellulose. And as you can see, it occupies a much higher volume. However, if I leave it in the lab for a couple of days to dry in room temperature, the structure completely collapses. So the swollenness is gone, so to say. And this leads me to my method and concept that I've been working on during my PhD. So what we do is a cold alkaline swelling, and then we do a reprecipitation with acid, and then we do some thorough washing. And after that, we have our swollen cellulose. Great, but there are still some issues with this swollen cellulose. First of all, it binds a lot of water, and water can be an issue when we want to produce derivatives because it dilutes the reagents or even disturbs the reaction. And then we have something called hornification. So I showed you the collapse of the fiber when we dried it, and this is called hornification. And hornification is a highly debated topic, and we do not all agree on the mechanism. But what we can agree on is that it makes the fiber hard and stiff, and that it makes it unable to reswell in water. And what is most important for me is that it significantly reduces reactivity. That leads me to my aims and objectives of this thesis. So first, we wanted to see what structural changes do we have when we do our alkaline swelling and reprecipitation. We also wanted to study the effects of drying, so do we get hornification, and how can we preserve the swollen structure? Of course, we wanted to evaluate the changes in chemical reactivity, because that was the main topic of the project. And then we also looked at, can we use this alkaline method to upgrade paper-grade pulp to more valuable pulp source? And for my last project, I wanted to explore waste source. So we wanted to see if we can use recycled textile with my method and see if we can increase the reactivity. And of course, we have to align our project with the UN sustainability goals. And this project targets goal number 9, 13, and 12. So further on in this presentation, I will talk about the projects, or actually the papers, depending on what cellulose source we've been using. So for the first part of this project, I used microcrystalline cellulose. And microcrystalline cellulose is a rather short-chain cellulose that we can use as a model compound to just see how, or predict how it's supposed to look. Later on, I used kraft pulps, and we used both softwood and hardwood pulp. And softwood are those trees with needles, so I had a mixture of pine and spruce. And hardwood are those trees with leaves, so I had a birch pulp. And these are a bit more complex materials because they have other wood components and they have a higher degree of polymerization, meaning the chains are longer. Then for the last part of the project, I used a waste source, so we used industrial and post-consumer waste recycled textile. So let's start with the reactivity of the microcrystalline cellulose. So I did my swelling, I got this amazing highly swollen material, and then I tried to do some carboxymethylation. And as you can see here, it did not work. So on the wet material, the carboxymethylation reaction is an ether reaction, so it did not work together with water. And then when we dry it, we see the hornification effects. So it was not even as reactive as the reference, so it's better to just do nothing. However, my colleague at Karlstad University performed oxidation, and oxidation followed by cationization. And here she could see that if we have the wet material, it is more reactive than the reference. There are also different scales on these graphs, and that's because we measure the reactivity in different ways. So for carboxymethylation, we measure the degree of substitution, and for the oxidation and cationization, we measure how many charged groups we have introduced. But it seems to work when we can perform reactions in water. So we wanted to know how can we preserve this swollen structure without causing hornification issues. leading me to my drying study. So we wanted to evaluate 3 different drying methods and see if we could preserve the swollen structure and increase the reactivity and preserve and have the reactivity. So we did freeze drying, glycerol drying, and acetone drying. And here, glycerol drying is when we have glycerol in the system as a spacer, hindering the cellulose-cellulose interaction. So it's still something that is in the sample, and it doesn't evaporate away. And for the acetone drying, we did a solvent exchange. And freeze drying is something that maybe not is industrially applicable, but we still can do it on a lab scale. And we measured how swollen is the material after the drying. So we measured this by using water retention value. And water retention value has previously been shown to correlate very well with the degree of hornification, but also it tells us how much water the sample can bind. So what we can see is that if we don't dry the sample, we have a very high water retention value, and when we dry it in the presence of glycerol, the water retention value remains high, meaning we have preserved the swollen structure. Whereas for freeze drying and acetone drying, it was slightly reduced, but it's still better than if we don't treat the material with the swelling. And now I will show how reactive the materials are after the drying methods. And to be able to compare them, I mentioned that we measure different things. So I normalized the values so that we can compare them in between each other, because we have 3 different reactions and we measure reactivity in different ways. So for the freeze-dry material, I could see that it's more reactive in all 3 reactions. So for carboxymethylation, oxidation, and cationization, we get a higher reactivity compared to the reference, untreated material. However, for the glycerol dried, we could see that the glycerol is not a good molecule to have in the system, because it competes with the reaction when we do carboxymethylation. Because glycerol also has an abundance of hydroxyl groups, so we don't want to react them instead of reacting the cellulose. Air drying, I already told you that this does not work due to hornification effects. And then the wet sample only worked for the oxidation reactions and cationization. And then we looked a bit at the structure. How does the structure change? Can we connect this to the reactivity? What we could see was that when we look at our particles or the microcrystalline cellulose in optical microscopy, we can see that they are quite sharp edges, and we still see some type of what could be fiber morphology. But what happens when we precipitate it after the swelling is that it becomes like a disordered mass, or at least that's how it looks in optical microscopy. But when we look at it in a cross-polarized microscopy, we can see that there is still some birefringence. And that's the white part of the material, showing that there is still some crystallinity left in the sample. We also performed X-ray diffraction patterns, and we could see that the reference here, that's the untreated material, is the light purple line. Here we have something called the cellulose 1 pattern, whereas for the other material we have a cellulose 2 pattern. So something is happening with the crystalline structure as well when we do the swelling and reprecipitation, which was kind of expected. And then we also measured or calculated the crystallinity index. Here it says CI percentage, and we can see that compared to the reference that has an 82% crystallinity, we lower the crystallinity, but we have to take into account that we also are measuring this using the Siegel height method, which slightly overestimates the values. So to summarize what we've been doing for the microcrystalline cellulose, I'm trying to connect them back to my objectives, so objective 1, 2, and 3, and we could see that we get the highly swollen structure, and we confirmed this by water retention value. And the methods that we suggested for drying, they work and they preserve the swollen structure. And we could also see that the chemical reactivity was increased, even after drying. So to the second part about the kraft pulps. I mentioned that kraft pulps are a bit more complex because they also have hemicelluloses, and the degree of polymerization, chain length, is longer. So what we did here is that we added a step before the swelling, and that was acid hydrolysis. And what we do then is that we try to cut the chains. So the acid hydrolysis lowers the degree of polymerization, or viscosity in this case. It's the same thing, they correlate. And then in any other sense, the protocol was exactly the same. So we swell, we reprecipitate, we dry, and we get our swollen cellulose. And when we look at the viscosity, that's how long, we can see that that's approximately how long the chains are. Then if we look at the reference here is an untreated material, so no type of hydrolysis or swelling. And then we have direct swelling, hydrolysis, and then we do hydrolysis followed by swelling. So it's a combination of two methods. And then we can see that the viscosity does not go down because of our swelling to a large extent. It drops a bit, but the most effect is the hydrolysis, which is of course expected and according to literature. And then we look at the water retention value again, so we want to see how swollen these materials are. And here it was rather surprising to see that the softwood sample responds better to direct swelling compared to the hardwood. However, when we do hydrolysis followed by direct swelling, we can see that they both have a rather high water retention value, so they are much more swollen. We also looked at the carbohydrate composition for these materials. That means we look at how much cellulose and how much semicellulose we have. And we could see that regardless of the type of method we do, we can see that for hardwood, cellulose content goes up, whereas hemicellulose content goes down. So we get the purification effect. However, for softwood, the values remain rather constant, meaning that we don't see that the hemicellulose is removed. And then we looked at the microscopy of these fibers, and we could see that the hardwood, after direct swelling, it looks kind of similar to what it did before the swelling. It just maybe a bit more swollen and also has some more kinks on the fibers. But if we perform hydrolysis and then swelling, we can see that there are these like patches of fibers where they've lost their fiber integrity, or they lost their morphology. So it's more disordered. And for the softwood, we could see the same, but in line with the water retention value, we could see that direct swelling is that the softwood responds better to the direct swelling, because we see these patches of disordered material directly compared to the hardwood. And for the combination of methods, it almost looks like similar to the microcrystalline sample in some of parts of the sample. And now for the reactivity of these materials. So instead of performing derivatization reactions, we did an acid hydrolysis, and we wanted to target or see how susceptible is the structure to acid hydrolysis. That means that we want to see how much glucose can we get out in the solution. And we measured this over time by taking out aliquots. So here we can see, just in line with the water retention value, that for hardwood you need to do some kind of pre-hydrolysis step to boost reactivity. But for softwood, we could see that, just like the water retention value, that it responds very well to the direct swelling, and we get a high reactivity directly. And now I'm going to go back a bit to the purity that I talked about previously, so the carbohydrate composition, if you remember this. So we saw that hardwood, when we do alkaline swelling, the cellulose content goes up and the hemicellulose content goes down, but the softwood remains constant. So we wanted to expand on this and also add some more mixing into the sample and see if we could remove more of the hemicelluloses during the swelling reaction. And then we precipitate, and then we wash, and then we do an enzymatic treatment. And this enzymatic treatment we want to add to see if we can push the purity further towards something called a dissolving grade pulp. And the dissolving grade pulp is something that we use for derivatives. So dissolving pulp and cotton linters are typically used because they are very pure. And we use the enzymes because they are highly selective and they do not degrade the cellulose. Looking at the results, we could see that for hardwood, if we start with 20% hemicelluloses, we could drop it down to 12%. And if we further push and try to purify with the enzyme, we get it down to 10% hemicellulose approximately. And for softwood, we saw the same trends. So we start with 12%, and then we reduce it to half, 6, and then we can further push it down 1 more percent. So to conclude about the kraft pulps, also targeting my objective 1, 3, and 4, we could see that swelling can reduce the hemicellulose content. And if we further add an enzymatic purification step, we can push it a bit more. And we also saw that swelling enhances the reactivity, and this could be a way to upgrade paper-grade pulps for future derivatives production. So to the last part of the presentation. Here we wanted to see if we can use a waste source. So recycled textiles is something that we have an abundance of, a lot of fibers in the system. Here we got an industrial and post-consumer waste textile. And the tricky thing about cotton, so these are based on cotton, is that they do not respond as well to an alkaline swelling or dissolution. So we wanted to expand the protocol a bit more, and here we used a freeze-thawing protocol instead. And what we do here is that we freeze the solution, the alkaline solution, and then during thawing we mix it very much, and then we get our suspension, we reprecipitate it, wash it, and get our swollen cellulose, just like before. So looking at these materials, we also had 2 virgin materials in this study. So we had cotton linters and dissolving pulp. As I mentioned, these are the typical sources we use for derivatives. And then the recycled textile, one was based on 100% cotton, whereas the other one was had a bit of synthetic fibers in them as well, but it was less than 8%. And we could see that the dissolving pulp and the recycled textile, they have approximately the same viscosity. So maybe they're more comparable to each other, but we also wanted the cotton linter in this to have a cotton source, a virgin cotton source. And we could see that the viscosity does not decrease that much from our alkaline treatment, which is good, so we do not degrade the material. However, the one with the synthetic part in it decreased by 18%, which is it's not that much, but it's still something. And then we looked again at the water retention value, and we could see that the swelling works well in our whole system. And we get a high water retention value, especially for the recycled pulps, which was very nice to see. And then we further look at the microscopy images of these fibers. And we can see that if we don't swell, if we have our reference material, the cotton fibers are very long and they have a quite smooth surface. And when we perform our swelling, we can see that they kind of coil and curl up. And this is very typical for cotton, so we did not see this in any type of wood-based materials. We could also see, maybe it's a bit hard on the projector, but we can also see that in the sample with some synthetic material, we can see that there are synthetic fibers that do not respond to the swelling as well. And then, of course, the reactivity. So here we measured reactivity in the same way as the pulp. So we measured the susceptibility to acid hydrolysis. And in this case, we could see that reference is the non-treated materials. They respond quite similarly and have a low reactivity. Whereas if you look at the swollen materials, they have quite good reactivity. And what was very interesting to see was that our recycled cotton performs better than the dissolving pulp, which is a typical material that you use for derivatives production. So we were very happy about this. And then to conclude the cotton part, we saw an increased accessibility and that we could swell the materials, and the swelling was better for the recycled materials. We also saw that we have a different type of fiber structure in the microscopy images compared to the pulp fibers. And we could see that we increased the reactivity across all materials, and this could enable the use of low value streams for higher applications. And now we're almost at the end, so I'm gonna conclude a bit the whole thesis. And I've chosen these 3 points here. Since I worked with so many different materials, it's hard to, but I wanted to have an overview. So what I wanted to say is that the swelling treatment can increase the accessibility, at least that's what we believe, and that we retain the viscosity, kind of. And then we also saw that if we enhance the accessibility, this will result in an increased reactivity across all invested feedstocks. And then we also saw that this method can provide a route to upgrade paper-grade pulps and also recycle textiles into more high-value precursors for derivatization reactions. And with that said, I would like to start by thanking the Knut and Alice Wallenberg Foundation through the Wallenberg Wood Science Center, which my project has been a part of. Also, the last part of this project has been funded by the Åforsk Foundation. Then I would like to thank my supervisor, Professor Monica Ek and Professor Gunnar Henriksson. And then I would like to thank the Department of Fiber and Polymer Technology, and of course my division and all my colleagues. And my co-authors, Björn, Morskan, Karl, Jenny, Alvaro, Johan, and Johannes. And also my friends and family. And of course, all of you here today, thank you so much for listening.